Hello, we are picking up the solutions to the Chapter 3 Mixed FIP quiz for physics. When last we left our physics heroes, they were on number 4, which is a non-perpendicular vector problem. And we had established that the drawing looked very much like this. Whew, really awful, because all of the triangles that you can make with this overlap one another. In a case like this, the easiest thing to do is to actually pull those triangles out and try to see your x and y displacements for each leg of travel sort of separately. So let's do that. Of course, we remember that overall what we're looking to find is our resultant and the heading, and that resultant will be equal to the square root of delta x total squared plus delta y total squared. So we're looking to find delta x total and delta y total. Delta x total is equal to the sum of delta x1 and delta x2, and delta y total is equal to the sum of delta y1 and delta y2. So the first leg of our travel, which is going to give us our delta x1 and delta y1, is 1.48 kilometers at 34 degrees south of west. That puts our delta x1 there, and means that delta x1 is equal to the cosine of theta times 1.48 kilometers. And as a handy note to myself, I try to remember to put that arrow in. That gives us a delta y1, which is there, and means that our delta y1 will be equal to the sine of theta times 1.48 kilometers. And again, as a handy reference for myself, I tend to draw in an arrow. You'll find those values, and we find that delta x1 is equal to 1.269, etc. kilometers, and that's to the west, though I've just indicated it with an arrow, and delta y1 is equal to 0.827605, etc. kilometers, and that'd be south. So again, I've just indicated it with an arrow. I'm going to set those aside and work on my second triangle. So the second leg of travel is 0.850 kilometers at 52 north of east. And I realize that in here I actually drew those reversed. It's even harder than it looks like, because in fact the x displacement is interior there, and due to the fact that it's adjacent to the angle, delta x1 is equal to cosine theta times 0.850 kilometers, and delta y1 is going to be here, right there, and due to the fact that it's opposite the angle, it's going to be equal to the sine of theta times 0.850 kilometers. Now you can find your values, delta x2 and delta y2. Geez Louise. You can now find your values for your second x and y displacement. Okay, we get a value for delta x2 of 0.5233, etc. kilometers, and it's eastward, though I've just indicated that with an arrow, and a value for delta y2 of 0.6698091 kilometers northward, though again I've just indicated that with an arrow so that I don't screw something up. Okay, at this point we're ready to compute our total x and y displacements. So because we already know that delta x total is equal to delta x1 plus delta x2, I'm just going to put in the values that I've already obtained. Since I'm handling this with the visual cues of arrows, rather than applying a traditional Cartesian coordinate system to the compass rose, I'm going to go ahead and make my smaller value negative, giving me positive numbers to work with. So the total, therefore, I'm going to subtract 0.5233, etc. from the 1.2269, or add a negative. Doesn't matter whichever way you want to express that. The value that I get for my delta x total is 0.703663353 kilometers, and that would be westward. Okay, now I'm ready to get the value of my total y. Okay, again, since I'm not using the traditional Cartesian coordinate system imposed on the compass rose, I'm going to make my smaller value a negative, which means I'll be either adding a negative 0.6698091, etc., to my 0.872, or I'll just go ahead and subtract it. In either case, the value that I get for my delta y total is the same, and it's 0.157796, etc. kilometers, and that would be southward. Okay, now I'm ready to make my overall triangle. I realize that my x resultant is a line like that. It's a vector that is pointing west, and the magnitude of that vector is 0.70366, etc. kilometers. The magnitude for my y total is pretty little. So I have a total y displacement of 0.157, etc. kilometers, and that's pointing southward. That gives me an overall resultant that looks like that. I'm going to draw the arrows on that in a different color just to make it stand out a little bit more. So I can find the magnitude of that resultant using Pythagoras. Okay, that's easy. I'm just referring back to the equation that we started off with. Resultant is equal to the square root of delta x total squared and delta plus delta y total squared. Okay, for that I get a value for my resultant of 0.7211392 blah 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 kilometers. Now, of course, I'm not done. There are two things I have to do. I have to look at my sig figs, and I have 2, so this will be 0.72 kilometers. But I also have to look at the heading for this vector. Remember that you're being asked what path should you follow to get back. So, while the total triangle I've drawn here with the arrows pointing as indicated shows you your resultant displacement, in order to get back home, what you actually need to do is to turn those arrows around and realize that from where you ended up to getting back home, you're going to have to follow that path. This turns on its head which angle is theta, and hence which trig function that you would use, well, not which trig function, but which displacement is your opposite and which is your adjacent. The easiest one to do is this angle, which of course gives you delta x total as your opposite and delta y total as your adjacent. So if we take the inverse tangent function of opposite, 0.703, etc., over 0.157, etc., our adjacent, that'll give us our theta. And we get a theta of 77.36, on and on and on, degrees. That would be east of north. East of north. Our final answer with sig figs is 0.72 kilometers at 77 degrees east of north. Of course, you're welcome to use the complement. Just be careful about which side you use as opposite and which side you use as adjacent. Okay, moving along. We have a kicked, flicked, and pushed problem here. So as always, to start out, we're going to list our variables on the x and y axis. So we're standing on a cliff kicking rocks, and we're told that you kick a rock off the cliff with a speed of 18 meters per second, and you're given the height of the cliff. What we want to know is how long it takes for the rock to hit the water below. Well, the interesting thing is that since none of the things that you're interested in are something that has a value apart, it has the same value on the x and y axis because you're looking for time. So given the fact that we have the initial velocity on the y-axis, that being 0, we have the acceleration on the y-axis, and we have the displacement on the y-axis, we can actually solve this without involving the x-axis at all. Let's pull out an equation that uses the 4 things that we're connecting here. Well, there's this old standby, but of course, since time appears in 2 different locations, it would be a quadratic solve, and that's a nightmare, except that it's not. Because VIY is 0 initially, we can get rid of that component, giving us just delta y equals 1/2 a delta t squared. If we were solving for anything that bridged the axes, we would have to use variables from the x-axis as well. But in this case, we're not, and we don't. So now we're ready to solve for delta t by doing some algebra. I skipped pretty much all the steps, but we multiplied both sides by 2 to eliminate the half, divided both sides by acceleration to move that over, and we're left with 2 delta y over a equals delta t squared. So we've taken a square root of both sides. Now we're ready to plug numbers in. 3.2559, etc. seconds equals delta t. So with sig figs, that gives us a final answer of 3.2 seconds is the time it will take for that rock to hit the water. Okay, next one. Okay, we're told that a potato cannon is fired at an angle of 42 degrees and the potato lands 212 meters away. What's the maximum height that the potato reached? This is one more of those problems where we're really looking at two separate portions of the travel. So we're going to start off by doing what we've always done and listing our overall x and y variables. Okay, so I've done the usual listing of variables on the x and y axis, but the thing that we're really missing is the point at which we're interested in is not the overall travel on the y-axis, where we assume the displacement to be 0 or near 0, but it's all of what happens when delta y is at a max, at delta y max. So some things are a little bit different at delta y max. VIY is still equal to sine theta VI, and acceleration on the y is still equal to negative 9.81 meters per second squared. But at delta y max, which is of course what we'd like to know, VFY momentarily goes to 0. Having that piece of information will allow us to key in on what we need. So we're going to start off just looking at the variables we have at delta y max. And we know that if we wanted to solve for delta y at top of flight, we could use the following equation. VFY squared equals VIY squared plus 2a delta y. And we could solve for delta y. Well, that's fantastic. Let's rearrange it. We know that VFY becomes 0 momentarily, so this gives us negative VIY squared divided by 2a is equal to delta y. Now let's not forget that VIY is really equal to negative VI squared sine squared theta divided by 2a equals delta y. Okay, that's great. That's fantastic. Wait a second, we don't have VI. Okay, so we're going to have to create an expression for VI using the information that we have for the overall flight. You've done this before, but it's a little tedious. So remember that looking at our equation for the x and y axis for the overall travel, we have, delta y equals VIY delta t plus 1/2 a delta t squared, the equation that we most commonly use to connect the x and y axis. And we have this expression for t built out of components on the x-axis. So that gives us the ability to do some algebraic magic. Delta y equals VI sine theta. I've just inserted my expression for VIY from there, from my list, times, and I'm going to insert my expression for time, delta x over, and I'm inserting my expression for VIX, VI cosine theta, plus 1/2 a, and now I'm going to square my expression for VI. So delta x squared, VI squared, cosine squared theta. Okay, I can do a bunch of algebraic magic, including getting rid of my VI's, taking my sine cosine and running a trig identity to make that tangent of theta. Let's do all that stuff. Okay, we're down to here, and by now you should be fairly familiar with the derivation to solve for VI. VI equals the square root of a delta x squared over 2 cosine squared theta times the quantity delta y times tangent theta delta x. Whew. Okay, now it's just a simple matter of plugging this expression right into our equation here. So since we're squaring VI in the equation for delta y max, we can remove the radical, and what that gives us is the following. Okay, we get a delta x squared over 2 cosine squared theta times the quantity delta y minus tangent theta delta x, all enclosed in parentheses, times sine squared theta, the whole mess divided by 2 times acceleration. That will give us delta y max. There is some algebra you could do to simplify that expression, but it's debatable whether or not it's worth it. When we plug our numbers in, which I'm not going to do here, we get a delta y raw value of 47.7214, etc. meters. In other words, a delta y with sig figs of 47.7 meters. Nearly 48 meters high. That's a high flying spud. Okay, that's it. I hope this is helpful, and if you have any questions, please email me.